Wanted to work through an example of propagation of light. This is propagation of light in a uniform material. Light propagates in a uniform material in a straight line. So, have you ever stood on the beach, looked out at the horizon, and wondered how far is the horizon? Have you maybe stood on a mountain, looked out in the distance, and wondered how far is the horizon? Or maybe on a plane, sat on a plane, looked out of the window and wondered how far is the horizon from the plane? The distance to the horizon, whether you're at the beach, you're on a mountain top, or you're in a plane, is an example of propagation of light in a straight line, and an example of some geometry to figure out the distance to the horizon. And this is the problem that we're going to figure out. Just a few remarks before I figure out the distance to the horizon. The horizon that I'm thinking about is the horizon that you would see across a flat ocean if you stand at the beach. The surface of the ocean is essentially the flat. The horizon that I'm going to figure out is if you stand in a desert, a flat desert, and that's essentially flat as you look across the sand. In real life, we look out at the horizon. There might be obstructions in the way, terrain in the way. There might be buildings, there might be trees, there might be hills or other mountains. So I'm thinking about a picture of the Earth, model of the Earth, or a situation with the Earth, where we're looking out at a flat ocean, we're looking out at a flat desert, and we're asking how far is the horizon in that case. A second remark. We're going to use the fact that light propagates in a straight line. Well, light propagates in a straight line in a uniform material. So light would propagate in a straight line if the atmosphere through which the light is propagating is uniform. In reality, the atmosphere is not always uniform. In reality, the atmosphere is affected by weather conditions. And so this is an approximation. We're approximating the atmosphere as a uniform optical material. Okay, so I've made a sketch of the situation. In the sketch, I've indicated the Earth's surface here, this curve. I've indicated you or me standing on the Earth's surface, this person here. I've indicated a few more lines on this sketch. I've indicated the radius of the Earth. The center of the Earth is downstairs here in the center of the screen. And this line here, vertical line in blue, represents the radius of the Earth. This line in red is also the radius of the Earth. This line in red is to the location of the horizon. And the line that defines the horizon is this tangent here to the surface of the Earth that intersects with the person, that intersects with the eyes of the person. And so this is a picture of the geometry when you observe or look at the horizon. The key thing about looking at the horizon is, well, firstly, what is the horizon? The horizon is the boundary between the Earth and the sky. It's the boundary between land and sky, or ocean and sky. So the boundary between Earth and sky, land and sky, is in this sketch located over here when this person looks from the left-hand side towards the right-hand side. That person is observing light from this boundary that travels in a straight line up towards the person's eyes. And so that's what we mean by the horizon. Again, for this orange line here, this is the line that the light travels along. We're assuming that this is a straight line. We're assuming that this is the propagation of light through a uniform atmosphere. Okay, so now I'm going to add some numbers and some symbols to this sketch. So firstly, the radius of the Earth. If you look up the radius of the Earth, it's about 6,400 kilometers. And so I'm going to add indication of that here, that this red line from the center of the Earth to the Earth's surface, this is 6,400 kilometers in length. We'll call that R for radius. I'm going to also add the sketch, the length of this blue line here. Now, I'm going to extend this blue line up to our eyes. So it's the distance from the center of the Earth up to our eyes, of which we're observing the horizon. This distance, I'll just denote it as R plus H. R is the radius of the Earth, so it's the distance from the center of the Earth to the Earth's surface, and H is the elevation of my eyes above the surface of the Earth. So this is going to be, in total, it's going to be 6,400 kilometers plus a little bit more, about 1.7 meters. That's the distance from my feet to my eyes. So these are the two lengths of these two sides of what actually is a right-angle triangle. You can see it here. Because this line that represents our view of the horizon is perpendicular to the radius of the Earth, here, this red line, or is tangent to the surface of the Earth at the horizon, this is actually a right-angle triangle. And so we know 2 or 3 sides of the right-angle triangle, and we want to figure out the remaining side, and that remaining side, let's call it the distance d. So at this point, we've constructed a diagram of the location of the horizon, and that's based on the propagation of light, a straight line. And from that diagram of the location of the horizon, we can extract from the geometry of the diagram an equation for the distance to the horizon. The triangle that we see in this sketch here has these two sides adjacent to the right angle, and then has a hypotenuse that's opposite the right angle. And Pythagoras' theorem says that for such a right-angled triangle, the square of the length of the hypotenuse, so that would be R plus H squared, would be equal to the sum of the squares of the lengths of the two other sides that are next to the right angle. So it's R squared, that's this side downstairs here on the right, and then plus H D squared, that's this side upstairs here. This is the distance to the horizon. And so this is an equation. If you look at it, we know the radius of the Earth, we do. If we know the height of our eyes above our feet, we do. Then we can solve this equation for D, the distance to horizon. So now it's just a little bit of algebra to solve this. I'm going to multiply out the square on the right-hand side, left-hand side that came from the hypotenuse. And now I've multiplied it out, let me make a few comments about this equation that we've created here. It looks pretty complicated, it looks pretty messy, but I'm about to make it simpler. Firstly, you can see that the R squared radius of the Earth squared on the left-hand side actually cancels with the radius of the Earth on the right-hand side. That's one thing that we can do to simplify this equation. The other thing that we can do to simplify this equation is to think of the scales, the relative scales, the relative sizes of some of the terms. We've got 2RH over here on the left-hand side, and then we got an H squared on the left-hand side. Well, RH is the radius of the Earth. It's a really big number in meters times the height of my eyes. H squared, on the other hand, is just the height of my eyes above my feet squared. So h squared is much smaller than 2RH. And so what I'm going to do is make an approximation. It's actually a very good approximation. I'm going to also ignore the h squared because it's so tiny compared to this other piece on the left-hand side. Well, now I've got a rather simple equation that just says that the distance to the horizon, if I take the square root, is the square root of 2RH, where R is the radius of the Earth. It obviously depends on the planet we're standing on. The distance horizon will be different on the Moon. It would be different on Jupiter. So it makes sense it depends on the radius of the planet. And it also depends on the height of my eyes above my feet, above the surface of the Earth. So it's also going to depend on whether I'm on the beach looking out at the ocean, or whether I'm on a mountaintop looking out at the desert, or I'm in a plane looking out at the ocean or the desert. So it's going to depend on the elevation, the height of my eyes above the surface of the Earth. And you'll notice here that we would see to a greater distance, the horizon would be a greater distance if the planet was bigger. If R was bigger, we would see the horizon at a greater distance. Also, we see to a greater distance if we're taller, or if we're on a mountain, or if we're in a plane. We see the horizon at a greater distance, because as R goes up, H goes up, then the distance to the horizon, given this formula, will go up. Let's use this formula and calculate the distance to the horizon for a few interesting examples. In this first example, I've plugged in the radius of the Earth. So I'm thinking about Earth now, not the Moon or Jupiter. And I've plugged in the height, 1.7 meters, of my eyes above my feet. That's the elevation of my eyes. So this is me standing on the beach, or you standing on the beach, approximately me, approximately you, standing on the beach, looking out at the ocean, looking out at the place, the horizon where sky and ocean meet. And we figured out by plugging in the numbers that it's about 4.7 kilometers away, or that's a little under 3 miles away. That's the distance to the horizon when you're looking out at the ocean from the beach. In this second example, I imagine that I've actually gone to the United Kingdom, and I've gone to southern England. I'm standing on the White Cliffs of Dover. And there's a rumor that on a clear day from the White Cliffs of Dover, which are about 22 miles from France, you can actually see across the Strait of Dover to France. So I want to see if that's possible, if the horizon is that far away, or if it's impossible because the horizon is not that far away, 22 miles. So I've plugged into my equation. I plugged in again the radius of the Earth. We're still on Earth, not Moon or Jupiter. But I plugged in 110 meters. That's the approximate height of the White Cliffs of Dover. And if you plug in that number, you discover that the horizon is now further away. It's 37 kilometers away. And 37 kilometers is about 23 miles. So it is actually possible, whether it's going to be good, whether it's going to be clear, to see France from England. My final example is I'm imagining I'm in a plane, I'm looking out the window, I'm in the plane looking out the window at the ocean, and I see this beautiful horizon where the ocean is meeting the sky. How far am I seeing in that case? In this case, I'm plugging in not, the height of my eyes above my feet, but the height of the plane above the surface of the ocean. So I'm taking a typical number for that height, 30,000 meters, 30 kilometers height for the plane above the ocean. And I plug that in with in addition, the radius of the Earth. And if you do this calculation, I got 620 kilometers, and I got 385 miles. So this is almost, this is about 100 times further than you would see on the beach, looking out at the ocean. Well, this has been an example of propagation of light in a straight line. We use propagation of light in a straight line to understand something that's really interesting on an everyday basis. That is, how far can you see? How far away is the horizon? We looked at the problem if you're standing on the beach and looking at the horizon, we're standing on a cliff looking at a horizon, and riding in a plane looking at horizon. The solution to the problem was built on the fact that light propagates in a straight line in a uniform medium. And it was also built on a bit of geometry and a bit of algebra. So we were able to construct a right-angled triangle with one side involving the distance to the horizon. And we were able to solve with algebra that distance to the horizon. Now, another interesting point is that often in solving problems, we might make approximations. We made an approximation here. So we made this approximation that a term involving the square of your elevation was much smaller than a term involving the product of your elevation, the elevation of your eyes, and the radius of the Earth. In the cases that we looked at, when we're just standing on the beach, or when we're standing on the white cliffs of Dover, or when we're sitting in a plane, it's a really very good approximation. But if, for example, we were in the space station, which orbits the Earth at a much greater elevation, this approximation that the distance to the horizon is the square root of 2 times the radius of the Earth times your elevation or altitude, that would start to break down.